So I want to take an opportunity to show you a little bit about how the cell membrane works and what the chemical properties are of it that allow for things to be moved in and out of that cell membrane efficiently and effectively. And I guess before we do that, I want to give a shout out to the Center for Biomolecular Modeling, also known as the CBM at the Milwaukee School of Engineering, known as MSOE. This is a group of wonderful people who help teachers teach some difficult concepts. And so I want to give them a shout out because I'm going to use some of their models in this video. So what we're talking about here is the cell membrane. And one of the things that I want to make sure that you understand is that when we talk about the cell membrane, we're really talking about what, it can also be called the plasma membrane. But this is going to be true for any kind of membrane in a cell. And so it doesn't have to be a cell membrane or a plasma membrane. It's all made out of the same stuff. All this stuff moves around the cell. Sometimes it gets inverted, sometimes it doesn't. It's all kind of a beautiful story of how it's all related. But there are two major components of the plasma membrane, or any membrane, and those would be, actually I'm going to write the word lipids and proteins. Now, carbs, I'm going to put carbs in here, but I'm going to put it in parentheses here because carbs are really more part of the extracellular matrix, not the actual membrane. So there are two major parts of the lipid category, and those would be the phospholipids and cholesterol. And then there are all kinds of different proteins. And so what we're going to do is first focus on the phospholipids, and I'll go ahead and circle that so you know that that's really where we're focusing. We're going to focus on the phospholipids and look at what they look like, and then figure out how they assemble themselves so that the proteins can then come in and help them regulate what goes in and out of the cell. And that's really what we're focusing on here, is the lipids and the proteins. Alright, so the phospholipids have several different components to them. And so I'm going to go ahead and label them out here. So we've got a phosphate group. We've got a glycerol backbone, and we have two fatty acids. Unlike a fat molecule, which has three fatty acids and no phosphate group, a phospholipid, the phospho part of it, refers to this phosphate group. So let me show you what that looks like molecularly and explain this model to you, because we're going to build upon this kind of model throughout the year. So if we're looking at this model, what I see here is lots of different colors, and I just want to tell you the color scheme. I would jot this color scheme down. I'm not going to write it because I know it really well. I'm going to tell it to you. So the grays refer to carbon atoms, and these carbon atoms have associated hydrogens on them, but we don't typically draw those hydrogens unless they are really important for the story we're telling. And so the grays are carbon. The whites are hydrogens that we're choosing to show. That doesn't mean that there aren't other hydrogens around. The reds are oxygens, and the blues are nitrogens, and the yellow is the phosphorus. So this section right here, these red dots, these oxygen atoms, and this phosphorus, make up the phosphate group. Alright, so here we have two fatty acid tails, a glycerol backbone, and a phosphate group. And I'm going to show you exactly how these assemble themselves to make a phospholipid. And I'll point out that all lipids are hydrophobic, or also known as non-polar, and it's really because of these fatty acid tails. These are the two fatty acid tails. And notice that most of this right here is all carbon and hydrogen, We don't have oxygen or nitrogens here. We don't see any reds or blues, and that means that the electrons are evenly spread out around those carbons, making it nonpolar, which is the opposite of what water's characteristics are. Remember, water is polar. It has a positive and negative charge. So these two fatty acid tails do not bond with water, and therefore we call it hydrophobic or nonpolar. So they will not mix with water, and that's key. All of these other components that have these charges are more likely to interact with water. But what we need to do, I'm going to remove my phosphate group out of the picture. I have my fatty acid tails. I'm going to remove one, or mostly out of the screen, and turn my glycerol a little bit. This hydrogen is going to pop off of the glycerol backbone, and that oxygen will combine with this hydroxide group that came off of the fatty acid chain. So they'll come together and create, voila, water, and this will create a bond here. And so now we've attached one fatty acid tail to the glycerol backbone, and we got a water molecule out of it. So I'm going to move that up to the top left corner there. I'm going to bring in the other fatty acid tail, and the same thing happens. We get a hydrogen that comes off. We have a hydroxide group that comes off. They combine to make a second water molecule. A second water molecule. This fatty acid tail bonds to the glycerol backbone, and we still have, and I brought back our phosphate group. I brought back the phosphate group. I'm going to turn this a little bit, so it's going to be hanging off the screen, but that's okay. You know that this is a long chain of carbon and hydrogens. I've got this hydrogen that's going to pop off, and I'm going to pop off this hydroxide group right here. Sorry, the stickers are holding it together a little bit. Alright, so then these pop together. I get a third water molecule, and this combines there. And so let me rearrange this a little bit so you can see more of what I'm looking at. So now I have a full phospholipid with two fatty acid tails, the glycerol backbone, the 3-carbon glycerol backbone, and my phosphate group. And so now I have my phospholipid, and in the process of making this phospholipid, I was able to net out 3 waters. I have 3 water molecules that have come out. Remember, they're not going to be anywhere near this fatty acid tail, so maybe I should just move them over here, where they might be happier in this on the polar side of the phospholipid. Now, remember this part is hydrophobic, and so now I've got my phospholipid molecule, and it's a fairly large molecule. It's got lots of different parts to it, but it's not the largest that we will deal with. Okay, so we got our phospholipid. Sometimes we draw it like this. On a smaller scale, it's got our 2 fatty acid tails, and this side is red because there's mostly red on this side. On this side of the phospholipid, and it has a negative charge due to that oxygen, which is a polar side, and that polar side is more likely to bond with water than the 2 fatty acid tails. Okay, so let's draw this a little bit, and I'm going to minimize my camera here. So I'm going to scoot over to the right just a little bit over here. I'm going to draw it in yellow. And we have our 2 fatty acid tails. Okay, so this is going to represent my phosphate group. I'll do this in red. Or I don't think I have a red, I have a pink. Okay. So I'm going to do this just to keep the color coding. So got my phosphate group, and let me do this in gray. I've got my 2 fatty acid tails. My 2 fatty acid tails, and somewhere in here is my glycerol backbone. So instead of drawing each atom, we typically stylize it as a ball with 2 tails that come off of it. And that's our phospholipid. But there are 2 major terms that you need to be very familiar with. And one of them is hydrophobic. So this is also in chemistry, I think you learn it as this, nonpolar. So these 2 fatty acid tails are nonpolar. Remember, there's mostly carbons and hydrogens. The electrons are evenly spaced. And on the opposite end, we have a hydrophilic end. Okay, so we've got our hydrophilic end, which we call polar because water is polar. And if you don't remember that, I'm going to do a very quick sketch. So this is my oxygen. Remember, oxygen's red. My oxygen's red. My hydrogens are white. And because oxygen is 16 times bigger than hydrogen, look back at your periodic table if you don't believe me, it's 16 times bigger than the hydrogens, then the electrons spend more of their time around the oxygen atom, and therefore, because electrons have a negative charge, the oxygen end is negative and the hydrogen end is positive. And those are the 2 sides, and because of that we say it's polar. So if anything has a charge, let's say sodium ions, potassium ions, chloride ions, all of these things will bond to water. Whereas these hydrophobic fatty acid tails will not bond to water because they lack that charge. Okay? So there's a very important word that we use sometimes to describe that this molecule has a hydrophobic and a hydrophilic end. And that word is, I'm going to write it down here, is oops, that's not right. Sorry, it's been a long day. I'm sure you know the feeling. Amphipathic. And you know some other words that, like, an amphibian, amphipathic. Amphibian can live in water and in part of its life cycle, and on land for the other part of its life cycle. So it has 2 modes, and so that's what it means, is that there are 2 modes, I guess. And so here we've got a hydrophilic and hydrophobic region, so it's amphipathic. All right, has a hydrophobic region and a separate hydrophilic region. And I'm going to stop there on this video because I realize I'm already at 14 minutes. I'm going to have a second video that talks about how these phospholipids combine to make cell membranes, and then continues on to including proteins into that cell membrane diagram.